Excited about the camera actually working. Now I'm ready. All right, so a smidge for the recapping. So aerobic organisms. So that's like a big picture concept, right? I mean, you're eating a molecule of glucose in the presence of oxygen to make some carbon dioxide. So that is the net equation of what that would be. You take one molecule of glucose, 6 oxygens to make 6 carbon dioxides and 6 waters. That is we've looked at a whole bunch of like individual parts of this, like glucose, pyruvate, through the citric acid cycle. But this is the overall net equation of everything. For every one molecule of glucose, by the time we get to the end, we'll make our water. So it may not be obvious, but this is really a redox equation, which means it has 2 half reactions. So the first half of the redox equation is glucose turning into carbon dioxide, some protons, and some electrons. So if this is the equation, is glucose being oxidized or reduced if I'm producing electrons? It is an oxidation. That means we have to have a reduction half equation to balance this out. So what molecule is being reduced? Oxygen. Oxygen's being reduced. Oh, yeah. And if I added these back up, I'd get the original net equation back up here, right? Because the protons and electrons would cancel out. The 6 waters would cancel out. And I'd get back my original net equation. That looks vaguely familiar. So, where does this occur in the body, this oxidation of glucose, this one molecule of glucose making some carbon dioxide, protons, electrons? Okay, where does the glucose enter your cycles? Starts also with a G. Glycolysis, entered. Okay, so glucose has entered glycolysis. Are these the final 2 products of glycolysis? Where are these 2 final products come out? Okay. All right, so that first half occurs in glycolysis and citric acid cycle. This second half, which is what we need to balance out the whole equation, is what we're going to look at in chapter 15. The second half reaction so that occurs in our electron transport chain, which is chapter 15, which is what we're doing now. So the other half of the reaction is what we're going to examine. Okay, everybody looks pretty excited. Or asleep. Well, 50-50. All right. Maybe the excitement's just overwhelming your system. Is that what it is? Your body can't handle it, and so it's actually going into shock and shutting down. That I would believe that. I can see that. Yeah. Yeah. It could be lack of sleep or food, or it could be shock. That's why your hands are all twitchy. Your eyes are a little dimmed. All right, so we're going to review even more because I know everyone is not as passionate about redox chemistry as I am. I find that hard to believe because it's really just the best chemistry out there. But it's possible it's not your favorite. So we're going to go slowly through all of these kind of big concepts. All right, let's see here. All right, so this is what we just looked at, this redox reaction that releases electrons into the mitochondrial electron transport chain was this reaction. That's going to be the reaction that's going to donate those electrons to do other things with. What are the molecules, there should be two of them, that we use to transfer electrons? NAD and FAD. Okay. So we have to use these other molecules to transfer electrons. We can't just let the electrons go free. They're going to pass through these other molecules to get to where they need to go. All right, so the mitochondrial electron transport chain, guesses where that occurs? The mitochondria, good. Why would we want to use the mitochondria? Because that's where everybody else is. That's where the citric acid cycle is. That's where all our chemicals are. That's where our ATP synthase is hanging out. So, three big things about our mitochondrial electron transport chain for it to work. One, we're going to transfer electrons through our NAD+, FAD, and some other new molecules we're going to be very excited to learn about. Iron sulfur clusters and CoQ, coenzyme Q. So these two we know, NAD+ and FAD. But now we have iron sulfur clusters and CoQ, which are only found in our electron transport chain. These transferred electrons participate in a sequential redox reaction in 4 different enzyme complexes. So these are called complex 1, 2, 3, and 4. Easy naming. And during these electron transfer processes in complex 1, 2, 3, and 4, we're also going to transfer protons across a membrane to make a proton gradient. And we need that proton gradient in order to drive the ATP synthesis. So that'll be the last thing we look at, is making ATP. All right, my 2 seconds of biology. There's this thing called the cell. In the cell, there's a mitochondria. In the mitochondria, we have all of our favorite proteins. We got pyruvate dehydrogenase. We have our citric acid cycle enzymes. And we also have all the enzymes and redox proteins needed to do our electron transport team and oxidative phosphorylation. Let's bring it all on the screen at the same time. There we go. All right, so here's your zoom in of a mitochondria that you've probably spent a lot of time in other classes looking at, possibly. All right, so the mitochondria has an outer membrane and an inner membrane. So the outer membrane is what you would consider the outside shell. The inner membrane is this kind of wiggly membrane that has a lot of different edges on it that we're going to use to put proteins on. We have the inner membrane space, which are the spaces between the inner membranes. And the outer membrane is used to diffuse proteins back and forth across. Proteins up to 10 kilodaltons. So as we make things in the mitochondria, we're able to export some of them back out to the cytosol. The inner membrane space is often considered equivalent to the cytosol in that it has high concentrations of substrates. So it has that's where all of our substrates needed to do all of our cycles are found. So it has high concentration. So you can think about kind of like the cytosol. It's just a big soupy mix of all kinds of intermediates, substrates, ions, things like that. And finally, the inner membrane itself The inner membrane is permeable to oxygen, carbon dioxide, and water, which is good because those are the things that we should be exporting out of the cell as you use them. You send them back out. But it is impermeable to most ions, which is good because that's where we're going to want our proton gradient to form. So it has ways of exporting these molecules, but it won't allow ions to be exported without going through a protein channel. That is all the cell biology you need to know for everything else we're going to do in this chapter. That's it. If you want to take more, there's always more classes, just not here. Enough of that junk. Let's talk about some protein redox. All right, this table's in your textbook. For whatever reason, on your PowerPoint, you may be missing the first 3 half reactions. I don't know, it's a picture, so I'm not exactly sure how I managed to copy the entire picture out of the book, but 3 of them got erased. Weird. Computers, who knows. But if you're looking for it, it's on page 396 in your textbook. So, just as a review, a redox reaction transfers electrons. Ooh, does everyone have a calculator with them today? Take a second and find one. Maybe someone in your row will have one, because we're going to do some calculating today. A smidge bit of math. Nothing trickier than addition and multiplication. I say that in my Gen Chem class. not ready for addition and multiplication. Probably one or the other in that class. All right, so as a way back review, right? If you lose electrons, that molecule has become oxidized. Should sound familiar. If you gain electrons, you become reduced. Well, sounds vaguely familiar. So if I look at this example, we know that FAD is the oxidized form of it. FADH2 is the reduced form. And if I know those two facts, this is the reduced form, then this one has to be the oxidized form of Q. Because on both sides of the arrow, you have to have one of each. You have to have an oxidized and reduced on each side. But we're going to look at this even closer than that. So, I think most people agree with this. It's sometimes hard to tell where the electrons are going in a net reaction. Right, in this reaction up here, if you didn't know the FADH2 and FAD combination, you'd have a hard time predicting which one was oxidized and which one was reduced. But if we do two half reactions, we will see who is donating electrons and who is receiving electrons. So if I do two half reactions for this same guy up here, all right, that looks maybe more familiar. FADH2 turns into FAD plus 2 protons plus 2 electrons. And I can do the same for the Q. Q has to gain 2 protons, 2 electrons to become QH2. So it's easier to see that the FADH2 has lost the electrons because now they are products. So now FADH2, it's more obvious that that is being reduced. The Q is gaining 2 electrons to become QH2. And if it is gaining, it is getting oxidized. So more, if you get stuck, break it into some half reactions, and it'll be more obvious who's gaining and who's losing their electrons. I'm coming around to this table. So the likelihood of a molecule to transfer its electrons the likelihood of transferring electrons is based on what's called the reduction potential. where reduction potential is this, E standard state prime. I ran out of space on my paper, so I'm going to flip it over when everyone's caught up. Good. What we do is we compare values of E standard state prime. So the greater the value of that E standard state prime, the more likely that molecule is to be reduced. So if we look back at this table, it's actually in order of reduction potentials. So this table in your book. The molecules at the top have the highest E standard state prime, and down here the lowest. So the greater the value, the more likely this reaction is to happen, because these are all reduction reactions. So however you want to phrase that, more likely. So the greater the value, the more likely this reaction is to occur. Good so far there. Okay, so then thank you. So to determine the potentials and the concentrations needed in a cell to have a specific reaction occur, we're going to use the Nernst equation from Chem 109. Nernst in the equation. Look at that, Chem 109 just keeps circling back. That's one of the most important classes you've ever taken, especially if you took it with me, which like a third of you guys did. So, the Nernst equation, for those who possibly have forgotten what this was. The potential the reaction actually occurs at is equal to the standard state potential minus RT over NF, which I'll explain in a second, natural log products over reactants, or reduction concentration over oxidation concentration. What if these concentrations are equal? These are equal to each other, right? Because if it's natural log of 1, natural log of 1 is 0, which means this whole value is 0, which means E equals E standard state, which in the body is true just about all the time, that these concentrations will be so close to each other that in the body most of the time these two values are, if not equal, they are very close. But typically, we're going to use these values, where R is the gas constant in the joules per k-mole version of it, 8.314 joules per k-mole. F is Faraday's constant, 96,485 joules per volt mole. And the temperature, unless the problem tells you otherwise, we're going to assume 298. put one of these practice problems. Dust off your calculator. Find where that natural log button is. Probably haven't used it in a while. All right. Let's calculate the reduction potential of a substance, knowing the actual potential, the concentration of the oxidized and reduced values. Oh, and I also forgot N over here. N stands for the number of electrons transferred. So it's going to be a whole number of some sort. So for this reaction, we know E All right, so here's our equation. We know E, so it's given in the problem. And we're looking for the standard state. Big brackets. Because often order of operations is what messes people up. These kind of problems, not so much the plugging it in, but doing it in the wrong order. All right, so everyone should take a second and calculate. Make sure you get the same answer as I do. Maybe find something different than that. Okay. A few problems like that in your homework. So now you're good to go to do those over Thanksgiving break. Mostly just plugging them in. Plugging them in is the hardest part, like getting the right numbers into the right slots, and then the order of operations. I typically do all this stuff first, the RT over NF, and then obviously the natural log, and then get down to the end. Because that negative sign can be slippery. Sometimes you lose it. They're tricky to like squirt out of your hands. Like a greased watermelon, right? I'm excited about the next part. You may be wondering, how does this relate to thermodynamics? Because we've been doing all thermo in this last chapter, right? We're all very concerned about delta G. Don't you worry. We can calculate delta G from E standard state prime. Look at that. Connections all coming together. So, electrons flow spontaneously from a substance of low E standard state prime to high E standard state prime. Right, so the higher the E standard state prime, the more likely it is to be reduced. If it's more likely to reduce, then it has to oxidize somebody else. And so those electrons are going from unlikely to be reduced, but likely to be oxidized, to likely to be reduced. Because if it has a low E0, so these guys mean right, because kind of the more likely you are to reduce, you have a high value. You have a low value, not likely to reduce, super likely to oxidize. So that's how they're related to each other. Oh, B. Either way. Yeah, be oxidized. Like, become oxidized. However that phrase works best for you. I did not leave myself enough space. All right. We're going to get to the example. Leave yourself a little space. We're going to do a warm-up example before we do an actual example. All because I want to do as many problems of these as possible because they're just so great. Okay, so let's say right, we had the FAD-Q half reactions. I'm going to flip my page over because I got no space. No space. All right, so here we have on my table, I have FAD plus 2 protons plus 2 electrons makes FADH2, and its E0 is about 0. I guess E standard state prime is about 0. Our co-Q, which we haven't called it this yet, but it's ubiquinone. I'll write that over here. Q is the same thing as ubiquinone. It just, we get the Q from the quinone portion of it. So its half reaction has a E standard state prime of 0.045. So if our statement is electrons flow from low to high, and this is 0 and this is 0.45, which direction are the electrons flowing? FAD to Q or Q to FAD? FAD to Q, okay? I'll rewrite some of the information over here. And technically FAD can't transfer electrons. It's really, right, it's this version of it, the FADH2 gives up 2 electrons so Q can have 2. That's the right thought process. I'm zoomed in real far. There we go. Let's calculate the delta G. Yay. Okay. So, right, we had these two half reactions before. Like 10 minutes ago. We're going to pause right here and talk about the number one rule that is both the most confusing and the most often messed up in these reactions. So you see what I wrote here? I wrote FADH2 goes to FAD plus 2 protons plus 2 electrons. On your table, it is written the opposite way, right? It's written as a reduction. It's written because these are all reductions, but I'm looking at an oxidation. So you may be thinking, oh, this must be like thermo, where in thermo, if this is a delta H or a delta G, and I flipped over the equation, what would you do to the value? Don't do that. That is only true if it's an H or a G or an S. If it is an E, leave it alone. Don't change anything. Just write down the value with whatever sign it comes with. It's not a standard state function. That's the tricky thing. So like it's not a G or an H or an S. It's not a state function. And so by flipping it over, it's concentration dependent, so you can't use the same rules. So number one issue, typically. All right, so now we're ready. Ready to do some math. Don't even think about changing the sign. I'll come after you. Yeah. S. Yeah. It's thermo-related, but it's not thermo, so it's not a state function. All right, so all I've done is added up, right? The two half reactions, and then I added the delta G, or delta E. I think I'm all confused. Delta E, 0 prime. So we're good there, right? We found that. So now, here's our other super exciting equation we're going to use. So let's go ahead and plug that in. How many electrons are being transferred in this all together? 2. Mm-hmm. So all together, let me just double check that's right. 6, 2. If it is a negative delta G, what does that tell me about the likelihood of this reaction going? Right, very likely, right? Exothermic, likely to go. A positive delta E0 prime also means spontaneous, right? Because the larger the value, the more likely those electrons are to be transferred from one molecule to the other. And so a positive E or a negative G, spontaneous. Which makes sense based on this equation, right? If I have a positive value here, negative of a positive value makes a negative value.
So they'll always be inversely.
They should always be inversely related. Yep. And so they're also always going to be the same thing, right? So if you have a non-spontaneous, this should also be non-spontaneous. It's just a way to double check your work, make sure you haven't lost those slippery negatives. That these should be telling you the same thing. E and G should tell you the same thing. Just the signs are opposite. Yep. All right, let's do this one example problem, and then I'll let everybody go and ruminate over this over Thanksgiving. All right, so in yeast, right, we had our yeast reactions where alcohol dehydrogenase reduces acetaldehyde to ethanol, which now you're over 21, most of you can enjoy some of this over Thanksgiving, so you can be thinking about this over Thanksgiving, your ethanol reactions.
I'm in class today.
That's all right, just takes one time to skip.
She skipped the other day.
She totally skipped on Wednesday. Didn't tell me where she was going. All right, so I'm saying that the acetaldehyde is being reduced to ethanol. Right, it's losing electrons. So there's my reduction reaction. And remember what my cofactor has to be in these guys? 50-50 shot. Good choice, NAD+. Good. And I'm writing these right off of the table. So acetaldehyde's right here, and NAD+ right there. So looking up their values, this has an E0 prime. So we always do these reductions minus oxidation reactions. I've written them both as reduction reactions right off the table. I wrote them both in the same direction, where the electrons are on the same side. But which one is actually the reduction reaction? Based on the word problem. We're going to reduce acetaldehyde to ethanol. So that's going to be our reduction reaction. So that value, actually let me write it a different way. It'll be, yeah, I'll rewrite it. That way it'll be hopefully less confusing later.
Get all these buzzets. Like that. Like.
Right, so I just flipped it over, but the values are the same. Is that better?
Are they backwards for NADH?
Let me see what I was going for. Yep. Yep. Well, yeah, I should have left that one. All right. Before I confuse anybody any further, we'll pause. We'll just pause. We'll come back to it. Cliffhanger.